So, the title of this paper is very interesting. It says, can two photon interference be considered the interference of two photons? Okay. So, this is very interesting title. So, this is by Pittman. He is a well known quantum optics person. Pittman et al. In fact, yeah, she is the last author. So, this is what is that? Volume 77, page number 1917, and then 1996. Okay. So, this is the paper they are talking about, and sorry, PRL. Okay. Okay. And okay, so I will draw the picture. Perhaps then it will be clear. So, this is time axis and this is space axis. Okay. So, now let us assume that this is the starting point, that means the source of the two photons. Okay. So, one is coming, one is going towards this A. So, this, so when I say A, this is your mode. Okay. So, this means the state is basically A dagger acting on 0. So, which is 1, okay, 1 A, and then the other one is B. So, B is the mode. So, basically your state is B dagger 0, which is 1 B. Okay. Right. And then you have, this is your beam splitter in the bottom. Okay. So, what happens is it goes by this direction, and then there is some time delay, and then it goes by this direction, and this is your D2 detector. This is D2. This detector is D2. Okay. And now here it is. Okay, like here. Sorry, so I'll have to erase this part, and then this goes to this direction. This is your D1. Okay, so this is my beam splitter. Okay, I mean, so what is happening is that, so you can think of this picture. So you have the source from which you have these two photons coming, one A and one B. Okay, and then you have mirrors for reflection, and here you put a time delay, which may be phase shift or whatever, which I call as tau AY. So, I should use here something like this. Yeah. So, this is my tau ay, and this is tau 1. I mean, this is according to their notation, basically 2 time delays. Anyway, so then it comes and then meet at a beam splitter. So this is my 50-50 beam splitter, okay, and then it goes to, I mean, there is some face plate etc., which we can consider, and then you put a delay here, you put another delay, and then it goes. So this is what is known as tau 1x. Okay. So here also you can put some face plate. So this is your D1 and this is your D2. So this is the schematic of this. So these are face plates. Okay, this is nothing to do. So these are in some angle theta 2, this is some angle theta 1. These are changing the polarization. Anyway, so this is my source of 2 photon source. So which is this point? This is your S, and then this is via A direction and via B direction, and then I put a delay here on the B part, on the which part? On the A part, you put a delay. Okay, this you can think of like here is the mirror, here is the mirror. So you put a delay which corresponds to tau ay, and then it goes through the beam splitter, and then you have a detector. Okay, and here on the B part, you know, it goes through the beam splitter like this one, and then you put a delay. So this delay is basically of the order of twice tau ay. Okay, and then you put a detector. Okay, so this basically tells you that again you get these I mean dip. Okay, so no coincidence between this detection and that detection. Okay, so this is what is going to happen.
Is it possible that initially something happened between the two?
Okay. So basically, of course, this is an experimental paper. They gave some kind of argument, but the basic thing is that, I mean, later people have explained that, you know, this is like your, which is called SPDC source. Okay, so SPDC source is, you have 2 nonlinear crystals put one after another. These are nonlinear crystals. So this means that your, you know, polarization relation with the electric field is not linear. Okay, so if you send light through it, the light will have polarization, but that is not linearly varying with respect to the electric field vector. So that is why it is called nonlinear. There are special types of these nonlinear crystals. Sometimes this is called, what is called, beta borium borate BBO crystal, then PPKYT crystal, some such things are there. So what you do, you send laser light, pump with laser. Yes. So this is about this paper that I was talking about last time, where okay, so you put a delay here in one path, and then after beam splitter action you put another delay here, and then you will get to see this HOM type effect, okay, like effect. Of course, there is a relation. I think this relation has to be satisfied. This
delay was not on the other path, it's on the same path.
This is on this path. Yeah, well, same or different, I don't know. Yeah. Okay. So you send laser light. This is called pump beam. So it has, let's say I choose a single mode laser light. So it has some frequency omega, right? Because single mode light, classical light you send. Most of the times this light will pass through, nothing will happen, most of the times. but occasionally what happens is that this will get splitted. I mean, need not be two spatially separated one, even in one single beam it may happen. So, it will get splitted, right, with the frequency omega 1 and omega 2. In fact, you can take them to be same, such that omega is equal to omega 1 plus omega 2. So, the energy conservation is there.
But the mode conservation is
Yeah, this is why it is a non-linear process. Okay, it is not a mode conservation, it is a non-linear process. Okay, it is not unitary, And if I look at the wave vector here, because the light will have wave vector, and this is my wave vector k1 and this is k2, then k should be equal to k1 plus k2.
that is like these are equivalent, right?
Yes, yes, this is, I mean, energy momentum, you can say conservation. Yes. So, so what happens is the state of this system. Okay, as I said, most of the times this light will pass through, nothing will happen, but very, I mean, rarely, I think of the order of 1 by 10 to the power 6, with this probability, the splitting can happen, and the joint state of this will be these two more squeeze vacuum state like thing, okay, right, and there, so what we assume here is that the source is basically sending one photon here, one photon here. So, what we are sure about is that here in, so this is called, sometimes it is called signal and this is called idler, I mean this is just name. So, in the signal beam you will have one photon, and correspondingly in the idler beam you will have to have one photon because of this correlation. Okay. If the signal beam has 2 photons, it will have to have 2 photons. If it is 0 photon, it will have to have 0 photons. Okay. So, I am assuming that this, so this is called spontaneous parametric down conversion.
But in you don't have mode conservation, so you can also have possibility like Q1 also.
Sorry?
Why don't you have the possibility of, let's say I put 2 photons,
Yes.
they do something into this.
This is, I am not talking photon, this is just a classical light, laser light, single mode. Okay. Yeah, here you can have possibilities, 2 photons here, 2 photons here, that is possible.
But I'm saying there might be a possibility of asymmetry, like 2, 1 or something.
No, I mean this particular case, it produces this correlated state. Okay. So, this people have verified this. I mean with this particular SPDC, I mean you can take some other nonlinear crystal, maybe that can happen.
With single photon, this thing will also do.
Single photon means?
Like I will inject only single photons. Like let's say I put like 10 to the power 6.
Yeah, possible, yes, yes, possible. But the state has to be in this case this is correlated, like one photon here, no photon here, no photon here, one photon here, one photon here, 2 photons here, 2 photons here. So, that kind of correlation has to be there.
What do you have spontaneous parametric?
Spontaneous parametric down conversion, SPDC, I mean this is a particular name, okay, SPDC.
So what is the physics? Because of some scattering happening in the nonlinear crystal or something?
Yes, yes, yes. So, because of the non-linearity, I mean light gets scattered here basically, it gets splitted into 2 parts. I mean as I said, this need not be of different momenta, it can be same, okay, but basically 2. But what difference is, so I can take for example omega is equal to omega 1 is equal to omega 2, k1 is equal to k2, that is possible. But in that case, what is difference is in the polarization. So, if this is horizontally polarized, this has to be vertically polarized or vice versa. So, there is a difference in polarization. Okay. So, therefore, if you put a polarizer here, then like a polarizer which is called PBS, okay, polarizing beam splitter, if they are same coming in the same direction, then horizontally, so generally polarizing beam splitter works in the way that it will allow the horizontally polarized beam to transmit and it will reflect the vertically polarized beam. Okay. So, then you can basically separate out these two beams. So, even if they are coming together using this PBS, you can separate them out. So, this will have horizontal polarization, this will have vertical polarization. Rest of the properties will be same. Here if you have one photon, you will have one photon. Okay. So, when they come together, this is called type 1 SPDC, and when they come separately, this is called type 2 SPDC. Okay. So, here what I am assuming is that my source is this SPDC, which produces one photon here, one photon here. So, that I am guaranteeing. Okay. Otherwise, these things will be messy. So, I am guaranteeing that this SPDC source producing one photon here, one photon here, right. So, basically what happens is that yes, this is a product state in terms of photon numbers, Fock states. What happens? Hello? What is connectivity problem? Okay. Can I talk now? Oh, okay.
To make sure you are connected to stable network. Yeah, that we are not.
What is this?
Okay. You have the arch to click. Okay, I understand. Record problem.
Anyway, I don't. Huh?
Pair of things produced, for example, in the case of photon, these are two more squeezed states.
Generally, that is the case. Yes. I mean, in terms of the photon numbers, but you can have, for example, correlation in terms of frequency, right? So, it is not that this W1 and W2 are fixed. Okay. So, this is the condition that you will have to satisfy. So, therefore, in frequency mode, I mean in terms of frequency degrees of freedom, these two states will be something like this. I do not know, maybe omega be omega f of omega, and then one is maybe, oh, this is omega naught, let me call it. This is omega naught. So, omega naught plus omega, and then omega naught minus omega. So, this you may call it signal, this you may call it as idler. So, in the frequency space, this is what you, and this is your difference in the frequency.
All the possibilities.
Sorry?
All the possibilities.
Yes. Yes, what is your question?
Since f of omega, I mean that's a function between, it's a correlated
Yes,
frequency.
yes, yes. So, this is what provide you, this is what it will provide you the correlation between the frequency in the signal and the idler.
But how do we know that if this is squeezed
This, so squeezing is not happening here, squeezing is happening in the Fock space. Okay. Okay, I mean you can have squeezing in mode in frequency mode also, but
Squeezing means essentially you are squeezing one like cakes or tea, right?
well, I should not say squeezing. Basically, the state will be in the photon number basis. This state, I mean this joint state, it will be of this form.
In phase, there will be asymmetry in the X and P, but then in the reflection of that will be there in the photon number also.
Exactly, exactly. Yes, yes,
Okay.
yes. So in the photon number case, it will be something like this: n lambda n n n, something like this. Okay. In photon, see, photons have several degrees of freedom. One is this number degrees of freedom. Frequency is another degree. Time bin is another degree. Polarization is another degree. So question is that this produces some kind of correlation, not just in one degree of freedom.
How time can be a degree of the
No, time bin, not time bin. So your basically light has always this coherence time within which you cannot distinguish between two light beams. Okay. So that will also provide you some sort of degrees of freedom. Okay. Yes.
It will give like more than 1 degrees of freedom, that correlation. Like,
Yes.
so like that this OM degrees of freedom also they are
OM generally it is not produced in OM. Generally not. What is the problem? Blow, huh? But is it, are you recording it? Okay, fine. What can be done? Yeah. Okay, good. So therefore you see that if I look at the state which is coming here, yes, in the photon number they are uncorrelated, but they have correlation in the frequency degrees of freedom. And because they have correlation in frequency degree of freedom, this delay will affect the frequencies. Okay. So delay is what? I mean basically it will change your phase, and that will depend upon the frequency also.
that will depend on.
Yes. So therefore, ultimately if I look at the state, if it turns out that after these two action I will get back the same state, then this is fine.
No, sorry, I did not.
Now after the action of these two delays, if I get back the same state which would have given me this dip, okay, then this will give you the same action. So this is exactly what is happening here, that in photon number fine, but in order to understand this effect you will have to look at it from the frequency degrees of freedom. How is it being, how this is being changed under the action of this frequency degrees of freedom, okay, and then we can see that. Yes.
That correlation now,
Yes.
that will have a role before that this beam split.
Yes. Yes. Yes.
But then that delay is after that.
No. That will have a role here, but then this delay will affect the frequencies. Okay.
But where is exactly your nonlinear system?
No. See, this is your AS. So AS means this entire process. Okay.
Oh, I see. Going to
So Atulya, this delay will affect this frequency, but this you see conditionally it will affect, right?
Yeah.
And then after the beam splitter action, it will again affect this thing. So there is a condition, I guess what I have written here, like these two. I mean this has to be double of this one. Then you will get back the same thing. Okay.
I'm a little bit confused about your statement that delay will affect the frequency rather the opposite. How I understand that if you have some delay or something, then you accrue an extra phase because of the frequency, because you have e to the power minus I omega t.
Yeah, but these are related. The why you are having change in phase because of this frequency. Okay, so these two are related there. So therefore, my point is that after this thing, okay, so well these two will have some effect that one can look at it properly. So, basically this state here will be same as what would have been the case, which is what, which was this state, right, 2 0 minus 0 2. So, of course, I am not giving you the complete description of this. Basic idea is this, that had it been just 2 photons here and they are uncorrelated, this could not have happened. So, you must have some kind of correlation in other degrees of freedom, otherwise this cannot happen. So, maybe what I will do is, so there is a follow up paper, or I do not know which one, maybe no, this is a before this one, this is before this one. So, there is one experimental paper and one theoretical paper. So, where again it is not been explained in full details, but in principle one can do that. So, this is the thing which we need to look at and do the work on our own to figure out what is actually going on. I mean, this is a rough picture, but what actually is happening, how this phase change is going to affect the frequency, that one can figure out. Okay. So, I will just give you these two papers, maybe. No, I mean essentially this is what is going to happen. So, the delay will change the phase, and the phase depends upon the. So, how will you act the phase, that depends upon the frequency.
So, if the beam splitter would not have been there,
Yes.
Do we get the same result? I mean, it seems like the beam splitter is not playing any role.
No, beam splitter action is needed, okay. Otherwise you will not get to see this thing, because then these are independent things, okay.
I mean, the only connection is in the initially they are correlated, and that's why we are.
So, let us say there is no beam splitter, and let us say you do not have these delays also, then what is going to happen? You will detect one photon here, you will detect one photon here, right, okay.
Chandan is saying that the online streaming has been stopped.
Yeah, you should mention to him that there is problem with the internet, okay.
So, I should say that the recording is going on.
Yeah, recording is going on, but the internet, there is problem with internet.
And this is the paper with this title, Can Do Photon Interference Be Considered? Is this?
Yes, this is the, no, this is not, this has not been done in that paper.
Okay, I see.
This is that is a later paper. So, let me give you these other papers where you can get to see that, but ideally we should do it properly, okay. I mean, this is just a guess, I mean kind of rough argument, that this delay will depend upon your frequency, or you can say it, how much delay you can give, it will change your frequency accordingly, okay. So, this is one experimental paper by Steinberg, okay. Steinberg et al. So, this is Paul Quiet is also there. This is in PRL, volume 68, P 2421. This is 1992, and then there is this another paper, which is again A.M. Steinberg, same set of people. PRA, okay. So, here you get the some kind of explanation, PRA 45, page number 6659, and then again 1992. So, in this paper you get this kind of explanation, okay. But it is not been given in details, one will have to do it. Okay. That is true, that is later, but I am saying the same formalism one can do there.
Okay, so here it is the formalism.
Here it is the formalism that your this SPDC produces these correlated photons in frequency degrees of freedom, and once we apply these delays, it will change this correlation in frequency accordingly, and that will give rise to the same again the same statistics. Okay. So, yeah, but I'll have to go through it, and we'll have to do it properly. Then this is the formalism one should use. Okay. So, yeah, so if you want to do that, you can take a look at it. Okay. Yeah. Okay, good. I mean, these people are all experimentalists, so they hardly care about poor theoreticians. Okay. Except it was this Mandel, I mean, he developed the entire quantum optics, but these are experimentalists, they just give a schematic and some sort of argument, and that is enough. We are poor theoreticians, we will have to understand it from the scratch. Okay. Okay, good. Oh, I think now this can be, I don't know.
You have been signed out for being inactive for 10 minutes.
What is that?
Like you were signed out now.
No, it's still not connected. Right?
No, internet is not that.
Yeah,
Oh, internet is not there, huh?
internet has not been.
Ah, okay, okay, okay. Anyway, fine. So, let us go back to this squeezing that I was talking about. I mean, I wanted to introduce this delayed choice because it is really intriguing, this and if you go through in details with this correlated frequency thing, you will figure out that actually the same interpretation will still be valid, that the photons are indistinguishable, okay, inside the beam splitter. The same interpretation will be valid there. So, basically what they have done in the experiment is that you look at the coincidence count. So, you remember in your in the Hong Ou Mandel, whether the original Hong Ou Mandel or with this delay. So, you will have to connect these two detectors with the coincidence counter. So, coincidence counter means that it will click if two photons come to the two detectors simultaneously. I mean, if they get detected simultaneously. Okay. Now, experiment is not like that. So, I mean, you may have, so maybe I will draw it once again. This is your source, this is coming. So, I will put a delay here, and then this is the beam splitter, and then there is another delay and then you have detector, right, and then you connect this with this coincidence counter. So, this will click if one photon is detected here, one photon is detected here simultaneously. This is how we call it coincidence count, and if they do not get clicked simultaneously, then this will not click, this will be 0, you can say. Now, experimentally this does not happen. What happens is there is a time window, let us say delta t, delta tau, here also a time window delta tau. Okay. So, within that time window, if one photon clicks here, one photon clicks here, we say it is the coincidence count is 1. And yes,
Even theoretically, like your path is delayed over there.
no, this is fine. I mean, path is delayed or not, that's a separate issue.
Then
My point.
anyway, you don't have simultaneous.
No. I'm saying even if you don't have these two,
Okay, I see.
still you will have, coincidence count theoretically means this should be clicked simultaneously, but that is not the case. Experimentally, you should give a time delay here. Okay. So, within this time window, there should be one photon clicked here and one photon clicked here.
And the numbers have to match one to another.
Yes, number should match. Yes.
It should be nearly simultaneous as well as the numbers have to match.
Yes, exactly. Yeah. I mean, number matching, you can look at the current it produces. Okay. Photoelectron, how much photo current it produces. Okay. I mean, I am assuming that there is no dark count, etc., no extra photon is coming here. In other words, I mean, this doing experiment is much more difficult than just telling about all this. Okay. So, so what you can do is, so therefore, if you repeat this experiment several times, right. So, you will have coincidence count, some of them you will not have. So, you can figure out like a ratio of the coincidence count. I mean, let us say I have done it n times, and let us say 10 times coincidence count has been clicked and remaining it will not happen, let us say. Okay. So, now if I plot if I plot this, so this is coincidence count. And this is the delay. This delay means how much delay you are producing, giving. This is not the delay, I mean this is fixed. Okay. This we have taken in our experiment. This delay is here. This is the delay I am talking about. Okay. So, what happens is that in the standard Hong Ou Mandel case, so let us say yeah, maybe I should plot here itself. Okay, then things will be easier. So, let me call it as coincidence count. Okay. So, what happens is it will behave in the Hong Ou Mandel effect, it will behave like this symmetrically. Okay. So, at 0 delay time you will have this dip, this means that coincidence count will be 0. This is in the Hong Ou Mandel setup without these delays. Okay. Yes. So, if there is no delay between these two paths, then we know that the coincidence count will be 0.
Oh, 1 will not be there.
Yes, yes, right. Okay. But now if I put a delay, like here I put a delay, forget about this, I put a delay here, then what happens is you can still get to see coincidence count. I mean, you can still get to see this kind of behavior, but now it will be shifted.
What you did right now?
So, now this is I mean, I do not know how to call it. So, this corresponds to with, so let me call it as tau a y, this is a tau 1 x, okay, something like this. So, with this delay. So, this is for Hong Ou Mandel, this is for something related to tau a y. So, where you have put this is not there, you put a delay here.
So what is on the x-axis?
This is this time delay. So, time delay is how much delay you are putting here.
But that's the label of the graph.
Yes. So, now the point is that this is in the case where you do not put any time delay here, okay, in the regular case. So, yeah, so actually, yeah, this is kind of misleading, okay. So, in the regular case, okay, let me put it in this way. So, in the regular case, you see, let us look at here, forget about this curve. So, if I look at here, there is some delay, So, this delay will give rise to coincidence
over there.
over there, right. This is less, but not 0.
So that is
That corresponds to this one, sorry, yeah,
tau AY.
yes, yes. So, yeah, so this you may call it as tau AY. So, therefore, it will give you some delay here, okay. Okay. Now, if we put this delay also, so you can say that I can take this my origin, right. So, then it will get shifted here. So, that at this time of delay you get a coincidence, right. At this, so if you give this much of delay, then you have a coincidence. It may be not 100% coincidence, but you have some coincidence count. Now, if you put also this one, it goes back again here. Okay. So,
Kind of cancelling phase.
cancelling phases, yes, yes, it kind of cancelling phases.
Second graph was for tau of 1x.
Yes, 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 tau of 1x, yes, yes.
I mean,
So,
tau
and
of
then-
1x moves you backwards, right?
It should be backward. I mean, maybe I should not put in this way. So, basically point is that if you put this delay together with this one, then generally it will come back towards this, okay, depending upon your value. Okay. So, at particular choice of this tau AY and tau 1x, you have this 0 coincidence, and this is what we need to understand thoroughly through this correlation in frequency. Okay.
Now I see the difficulty to understand it.
Yes, what?
Now I see the difficulty to understand it.
Yes, yes,
Because now at the beam splitter they are not putting like they are not coinciding like together.
yes.
There is no such indistinguishability explanation.
Exactly, exactly, exactly,
I see.
exactly.
Now I get the point.
So, after you put the second delay, they will again become indistinguishable.
How is it possible?
How is it possible? That is the question.
Like one delay is actually before the photons are indistinguishable, one is after they became
Yes,
indistinguishable.
yes, exactly. So, basically that explanation survives still now, the indistinguishability of photons. So, that is what we need to establish. Okay.
Do you get this case like always? No, right?
Which case?
Like let's say I do this experiment. I am certain that this kind of thing will happen.
No, no, of course not.
No, right?
No, no,
So
of course.
there is a possibility that might be second delay is making their path again synchronized.
Okay. So, this theory is so developed that one can actually figure out how much delay you will have to put, I mean how to correlate these two delays. Okay. That one can do.
No, not even correlating. I'm thinking of the explanation.
Yes.
So I'm saying that probably there is a photon which there is one here, here it is delayed. Probably they did not meet on the beam splitter.
Yes.
But on the way they have met in some way because in the second delay.
Well, see, I mean quantum mechanically we can, I mean this explanation that I gave, that is also not properly correct. I mean meeting does not make sense, we need to talk about the overlap of their wave function.
Yeah, that's what I mean.
So, essentially even you put this delay, this photon and this photon will pass through the beam splitter, but their wave function overlap will be very, very small.
Exactly. That means they don't meet. In some
Generally,
at least
yes. Generally,
Yeah.
yes.
But when you put that tau 1x over there,
Yes.
then like
They will have overlap in the wave function.
Yeah,
Okay.
that makes sense because the first guy was running very fast and then suddenly second guy was behind. Now first guy was after the beam splitter. Now first guy was running and you made him delayed. So now the second guy.
See,
has the chance.
Cheryl, the confusion basically what we have is that these are two spatially separated paths.
yes,
How can you have overlapping wave function there? Right? That is, I think that is the confusion.
I think my confusion is also that you mentioned that tau 1x is 2 tau AY.
I think that is usually, if I don't remember, if I remember properly, yeah. So there is particular relation.
There's a tau AY gap between time interval before, like, so that detector clicks for second and this one clicks first.
No, actually this twice you will have to take twice of this, because I think there is this question of double reflection and all that. So, that is why this has to be taken twice of this. Okay.
No, but do they reach the detector simultaneously then, or?
Of course, otherwise you will not get to see the same effect.
Yeah.
You will have to see. Yes.
If we consider these delays like for different tau a y and then different tau 1 x, we will get this coincidence 0 1 that detection.
Generally,
Then
yes.
we can consider another scenario where it will be like another tau a y and another tau a x. Like could be the tau a y could be more than, we can consider like tau a y 1, tau a y 2.
Yes, yes, yes.
Then we will also get this 0. Now, can we think like the operational that like value of these two things, whether it will be same or it will be different?
Which operational value?
Like in one scenario where we are getting like this tau ay1, tau 1x1. This is one state we are getting. Another situation with tau ay2 and tau 1x2.
Yes.
This is another state we are getting. Now, if we consider the operational value of first thing and the second that we are getting, could it be different or it would be same?
No, here operational value means what?
Like if this coincidence is becoming 0, means the state is having like that 2002, which
Yes.
is having a operational meaning in like quantum metrology as we know.
Yes, 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 yes.
So that operational meaning, whether it will remain same or
No, no, of course not. Of course not. I mean, because if you don't synchronize these two delays, in the sense that I think this is twice of this one, if you don't synchronize in this way, then the state, output state here will be different than 20 minus 02 by root 2. It will be different, and that different that will be different correlation, and that will be useful for some other task. Okay.
Oh, okay. So my explanation does not. I mean, like it's completely wrong. My explanation, my understanding was completely wrong. So now the problem is that they did not coincident on the beam splitter simultaneously.
Yes.
So they did not have any chance to overlap. Now
A little bit of overlap, because quantum mechanical wave function, we cannot say that it is just localized here.
okay, at least let's
Yes.
forget about the localized
I
fashion.
was trying to connect this amount of overlap in different scenarios.
Yes, that has to be the case. Yes. Yeah.
No, but in the case like now one photon went completely different side.
Yes.
Now I am putting delay here. How you can influence? So am I assuming in some way that these two paths are also correlated? Like on the way they have become some correlation or something.
See, the paths are correlated in the form of the frequency. Okay. So that is the only correlation one can think of here.
Yeah, so that means it does not work here. Like the explanation I am trying to put. So indistinguishability, how it is playing there. My problem is there. Like one went, okay, the one went there and I am here, but still we are.
Yes, this is what I told Cheryl. These two paths are spatially separated, and thereby the corresponding photons are indistinguishable. Okay. That picture here it is difficult to apply. So, more appropriate thing will be indistinguishability in terms of frequencies. Okay. In the frequency space, you talk about indistinguishability there. See, in the Hong Ou Mandel effect, we did not have to invoke indistinguishability there. Sorry, we did not have to invoke this frequency picture there. Okay. That is not needed, because we could have understood it through this. I mean, in principle one can do it with frequency picture also, but the point is this was much simpler in the Hong Ou Mandel case. Here, because of a delay, I cannot it has relation on the path, but effectively the correlation of the path has to be understood in terms of the correlation in the frequency.
No, but correlation of frequency does not mean they are indistinguishable.
Of course not.
Because you have different
Yes,
degrees of
but the point is, if their correlations are, if their frequencies are same once they come out of here, okay, and if you have no other degrees of freedom to distinguish.
But that is not the case. You have two different paths. That means you have 2 degrees.
So,
of
this is the point. Point is that in this picture, I mean we will have to do it properly. In this picture, this path that they are going into different paths, that has no role. I mean effectively that has no role. What role you will have to look at is through this frequency. I mean my point is that same frequency picture one can apply on actual the original Hong Ou Mandel effect also. So, this path is a kind of misnomer here. So, one should understand it properly how this SPDC produces the state, okay, 2 photon state. So, that is how one should understand it. Yes.
One question, what is the role of the beam splitter here? What is doing? I mean, if we're talking about the
Yeah. So, the beam splitter acts. So, this basically mixing kind of,
so I mean,
or mixing, or you can say superposing, whatever.
so if it had not been there,
Yeah.
and if photons would have come close,
Yeah, then you do not have all this all this drama here, it will go to one photon will go to one detector, another photon will go to another
so
detector.
in that case, if the photons will come close, we cannot say that they are indistinguishable.
In space, yes, but my point is that of course that is true, but this actual explanation should be given in terms of this frequency picture, then things will be much more clear. See, in space, how will you correlate these paths? What is the correlation between these paths? Then you will have to look at this can be mean free path or something like that and do that. That is much more difficult problem.
And using frequency, you have explanation, I believe.
Yes, maybe there is some other degrees of freedom you can have another explanation, but my point is within using this path degrees of freedom it will be much more difficult here. Maybe one can do, but it is much more difficult, because as soon as you associate a photon with this path and another photon with this path, they become indistinguishable more or less. Sorry, they become distinguishable. Okay. So, that picture will not work here. So, what we need to look at is do the similar argument for Hong Ou Mandel effect with the correlated frequency degrees of freedom. Then we can perhaps understand it more better, in a more better way, in a more complete way. I mean, yes, we do this explanation through paths, but giving the explanation through paths here, it becomes quite difficult. At least to me it is quite difficult.
I don't know how to even explain this. But the frequency picture is also not very physically satisfying. Maybe it is giving the answer.
No. I mean, if you do the experiment with SPDC, this is the kind of frequency, I mean correlated frequency that they produce, okay, right Atulya? I mean the experimentalists, they have also done this thing, right? So, they produce this correlated frequency. Yeah. So, this is what they do. Okay. So, sorry that I could not give you the full explanation, but I guess with this frequency correlated state one can give the explanation, but with this path one it will be much more difficult. I mean you can think of this path just to assign the mode, okay, that this is signal, this is idler, something like that.
In terms of frequency, just before this beam splitter, we will have just an additional phase, no?
Yes.
Then if you apply that beam splitter also, what will be the output? I mean,
So, these frequencies will get changed according to that phase.
In this case where tau 1x is 2 times tau y, we are assuming that this is 50-50, right? Let us
This is 50-50, of course this is 50-50, yes. I mean if you do something else, then you will have to do it
we
properly.
have to adjust tau
Yeah,
y and tau
exactly,
1x.
yes. No, to put it in the same picture of Hong Ou Mandel, you will have to take 50-50.
Yeah.
Okay, good. So, the last time I said that there must be some, the reason must be somewhere like in correlation, okay. Otherwise this kind of phenomena cannot happen. Okay. Okay, so let me go back to the squeezing part once again. So I think it will be a good idea to have a separate discussion about these works. Okay, I think Cheryl said that she will discuss it. Okay, she will have to read. Okay, and yeah, I mean all of us can read, of course. Okay, so what is that? Squeezing. So I discussed about the single mode squeezing. So this is another Gaussianity preserving transformation. Where your variable x goes to x e to the power r, but one should be careful what should be the corresponding Hamiltonian. P goes to, and now e should, it does not matter, but point is, yes, so e to the power r, okay. And then the corresponding Hamiltonian, squeezing Hamiltonian SQ r, this was what? R by 2 xp plus px, right? For this case, I guess so, right? Minus r and r, okay. And then if you write in terms of this a and a dagger, it will be r by 2, I think a dagger square minus a square, is it correct? There is I, huh? Okay, yes, iota. Yes. So the unitary SR is exponential of minus I H S Q R, which is exponential of r by 2 a dagger square minus a square, right? Whether I take plus or minus, plus iota or minus iota, we will have to see. Okay. And this is basically a scaling transformation, single mode scaling transformation. And you agree that this is a canonical transformation, right? And as a result, one can figure out what is the corresponding unitary representation. This is one representation. Okay, right. And the transformation is from a dagger to, it goes to cos hyperbolic r, sin hyperbolic r, sin hyperbolic r, cos hyperbolic r, a dagger, and this is your SU11 matrix. Okay, 1 plus 1 dimension. Okay, good. Right. Yes, what is the problem?
I am saying that, was there any minus sign nature? No. Okay. Shandeep is saying no, that means no.
No, previous one doesn't have.
Oh.
But in the textbook there was minus.
Oh.
There was a minus inside the system.
And the transformation.
Yeah, R if you take it minus R, that will become like that. Like in the definition of x, if you take x e power R, then there you'll get since.
No, but then another sign nature will be also minus.
Okay, let's see whether this is, let's see whether it is correct or not. So exponential of this r by 2 a dagger square minus a square a exponential of minus r by 2 a dagger square minus a square. So what will be this? This is A 1 by factorial 1. What is this? This is this is minus R A dagger, right?
This one will be A dagger, that means minus R by 2 A dagger.
No, this and this.
Exactly, minus R by 2 A dagger.
Do you have water? No. Thank you.
No, you are correct.
So, this one is R by 2 A dagger square minus A square. Now, what about this? This is plus.
Minus 2A.
No, this is minus minus, so plus. So, this is so this is basically R A, right? So on. So, this is E and this part, as I said, plus minus R by factorial 1, this is E dagger, plus this R, no, this should not be R, this is R square, R square. So, R square by factorial 2 A plus so on. So, this is your cos hyperbolic R A and minus sin hyperbolic R A dagger. Okay. So, if I use this, then it should give you this expression. So, therefore, if I use this. Now, if I do not use this, if I use what is it that I have used?
Your scaling must be changed. I mean, like, I think your expression is right on the right.
So, then what we need to do is I need to apply here minus, here plus. Okay. Okay. In that case, this will be plus, because R goes to minus R, that is the only problem. I mean, this, I mean, basically this is the your Heisenberg picture one. Okay. So this is correct. Eh? Okay. Good. Right. So what we need to look at is okay. So this means that, you know, if you now so let us call this as R. So which is S of R. S of R is what? So S of R acting on the vacuum. So this is my S of R. This is in the Schrodinger picture. Okay. So this is called single mode squeezed vacuum state. Okay. Right. And as I said, this will have only the even Fock states in this expression. Now, if I, okay, now this is again a problem because in the same notation I am using here, for coherent state, number state, everything, but you will have to understand from the context. Okay. So, now if I look at delta of x square with respect to this R state. Okay. So, essentially what will happen is that this is whatever the vacuum state uncertainty is there in the position, that will be multiplied by e to the power minus twice r.
I see.
So, this will be delta x square with respect to the vacuum state and then times e to the power minus twice r. I guess so. I mean, this you can check. Okay.
Vacuum state saturates the.
Yes, uncertainty bound. Yes. And similarly, if you do this, so this I am not doing, you can check it. If you do it with R, so then again you can check, this will be delta p square with respect to vacuum state times e to the power plus twice r.
So how did calculate this mathematically? Delta x, I mean, write it in terms of a and a rather.
Yes, 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 yes. So, or you can write it in terms of how will you do that? Maybe,
In terms of AM data, it would be more convenient.
yeah, maybe you can do like, let me try to do it like this.
Because we have the transformation.
So, this is x square right, and this is your vacuum, this is s of minus r, because s r dagger is s of minus r, then x square s of r 0 minus 0 s of minus r x s of r 0 square, right. And what is this?
This is like A plus A dagger 1 by whole square by 1 by. Audio.
Spacing.
What was the action I said?
Yes, sir.
X
We can,
becomes x to the power e
inside
minus
x, we can put an x and s rather. Kind of thing.
I understand that. Huh? Sorry?
There is an x,
Yeah.
we can inside this x,
Is it not true?
s,
Exactly. As at the R, S minus.
This is not true?
This is true. This is true.
Yeah, this.
Yeah, so you have just take square of that. The same argument, s minus r x s r, then again s minus r x s r, okay, minus
It is like
okay. Okay. So, what you are looking at here, so therefore, there is no question mark, this is correct. Okay. So, what you are looking at here is that the uncertainty in position has become exponentially small compared to the ground state uncertainty, while the uncertainty in momentum has become exponentially large, right. And once your uncertainty is too small, you know that you can very, very precisely measure that observable, right. So, this is the effect of squeezing, and this has been realized in lab and people are using it every now and then. In particular for gravitational wave detection, this is very, very useful. Okay.
Every methodology will have some of it.
Yeah, not just every metrology will have, will have advantage. Of course, one should be careful while talking about advantage, because squeezing requires some amount of resource. Okay.
But if my goal is just to precisely measure, then
That is infrared energy, to squeeze infrared.
yeah, that's okay. But I can make it like precise enough to find a gravitational wave.
Right, of course. I mean, ultimately you will have to look at what are you looking for.
Yeah,
So, so if gravitational wave detection can be done appropriately using squeezing, however large squeezing you apply, it is good enough.
exactly.
Okay. So then I introduce these two more squeezing. In fact, one can have multi-mode squeezing also. So if you recall the Hamiltonian for this single mode squeezing, what was that exponential of? No, not exponential. What is that? R by 2.
I mean, A dagger square minus A square.
So this is quadratic. Okay. So one more thing for the single mode squeezing. So I said that the squeezing, basically if you take your P and X, so what squeezing does is it reduces the uncertainty in position, like too much, but at the same time it enhances this thing. So basically if you look at these at some point, I do not know which point, maybe this is the phase space point. So here this squeezing, it is like this. So uncertainty in a coherent state it was like this, it is like circular, because in x and p, and in fact in every direction the amount of uncertainty in the coherent state basis is same, right. In the case of squeezing, in this position momentum squeezing, what happens is this becomes like this ellipse. So that the squeezing in position is very small, while the you have enhanced uncertainty here in the momentum. But this is not very special about the quadrature. You can do squeezing in any direction. So here also you will have the similar thing. So for example, you can take your x theta, which is x cos theta plus p sin theta, and p theta is equal to, what should be this one? This is a rotation, right. So if you take that, and if you can also define that x theta goes to x theta e to the power minus r, and p theta, because these are conjugate variables, canonically conjugate variables r, then this can happen. Okay. So there the uncertainty will follow the similar thing. So this is a squeezing which is not along this quadrature direction. So how will you achieve that? So one way is that I mean, you can apply the standard squeezing, quadrature squeezing, and then you rotate it. So this is under r theta rotation, and this is p going to r theta rotation. So then you rotate it r theta. So this is squeezing. So this will give you x theta e to the power minus r, and similarly you can do this one, r theta rotation. This is p theta e to the power r. Okay. Now the question is, what is this one, r theta rotation? I can write down the rotation matrix, that is not an issue, which is this matrix. Okay.
I mean, they won't both give the same result, right?
Which one?
You have to rotate first, then squeeze, right?
Yes, they won't give you same result. Yes, because squeezing and rotation they don't commute. Okay.
So this won't be x theta e to the r. It would be more like x e to the minus r cos theta plus p e to the okay, it's e to the r one place, e to the 1 minus r in the other place, right? So those two will be.
Yeah, I mean basically you can do either first squeezing then rotation, or you can do first rotation then squeezing. They are not equivalent.
They are not equivalent, yeah, because there it should be e to the r. So those two
Okay. Yes.
they will be different answers.
Yes. Yes. So the question is, how do you? So this is also a canonical transformation, right? This rotation. So what will be the corresponding unitary transformation for this? Okay. Like every time we do a canonical transformation, we will have to look for a unitary transformation, right? Okay. Yes, beam splitter does not produce this rotation. What does it produce, beam splitter? It does not produce this. Yeah, but at the level of field, if you do it at the level of quadrature, this is 2 input, 2 output. Yeah, so we have basically a simple one, which is exponential of this operator. And what is this h theta? H theta is theta or theta by 2, we will have to see. This is A diagonal A. So this number operator, if you take, that will give rise to this rotation. Okay. In fact, you can figure out that if I apply this exponential of I h theta, you can see what will happen. Okay. So this is again quadratic. So this is Gaussianity preserving. Okay. Right. So okay. So therefore, single mode squeezing case, it is not necessary that you will have to only consider the quadrature observable. You can take a rotated version of that also. Okay.
We can do squeezing in the spin system also.
Yes, spin squeezing is also possible. Yes. Yes. Yeah. So now two mode squeezing, when you talk about two mode squeezing, this is, I mean, one can talk about multi mode squeezing also. So this is
I remember you said last time that if you have one mode squeezing and if you have beam splitter, then you can generate any mode squeezing.
two mode of course, and from that two mode you can do multi mode also. Yes. So basically the idea here is that in the single mode case, we look at the squeezing of the quadratures, single mode quadrature. Here you look at two modes. So xa plus xb, it goes to e to the power minus r xa plus xb, and pa minus pb, it goes to e to the power r pa minus pb. Question is whether this is a canonical transformation.
Back him, I don't know if they have a class or something.
Oh, you have a class? At what time?
3:30.
3:30. Okay, okay. I'll finish.
Sure, no worries.
Okay. So now this is a canonical transformation. You can verify everything. Okay. In fact, not only that, you can also have something like this.
they
Yeah.
are canonically convergent.
So, yes, so this is a canonical transformation, right, and you can verify that this is not difficult. So, this is a canonical transformation. And this canonical transformation, of course, then one should look for a unitary representation of that. Now,
Suddenly, how it become xa minus xb as e to the power r?
what is suddenly?
Like xa plus xb, you had e to the power minus r, right?
Yes, yes, yes.
Xa minus xb, how it could be e to the power r suddenly?
Yeah, that is, I mean, you can take, see, the thing is, these are consistent, this canonical transformation. Okay. So, once I write down the Hamiltonian, then you will see that these are consistent one. Okay. So, it is not that, you can put, you cannot put arbitrary thing here, you will have to put this one.
In the first case, like squeezing is in the extent, I mean, then the enhancement in the P and the similar.
Exactly, exactly, exactly. So, if you look at these two, these are commuting observables.
Yes, yes.
Okay. Unlike in the case of single mode.
Unlike in the case of single mode, yes.
On the other hand, these two are also commuting,
True,
right?
true. So what I expect that they should be the same.
No, I mean,
XA and PA won't commute, right?
huh?
They won't commute, right?
Which one?
xb and pv will give you a class h cut.
Okay, okay.
So
The
both
other
h
one,
cut
yes.
they will come. That is why you have 1 plus 1 minus 1.
So, now, I could have done this similar thing as we have done in the case of beam splitter, that you split the transformation matrix and then look at its a unitary representation for the individual part, but that is much more difficult and I do not want to do that. So, what I will do, because that is, so what I do is is a layman's way of doing it. So, what I will do is so we will get some Hamiltonian, and this Hamiltonian is so this is two mode squeezing, okay, TMS. So, this will be basically R by 2 A dagger B dagger minus AB. Okay. So, oh sorry, it should be some iota here.
It is still quadratic.
Sorry?
It is still quadratic.
It is quadratic, yes, it is still quadratic, yes. Squeezing is a Gaussianity preserving transformation, it has to be quadratic.
A square, a dagger square and a square.
Now, what you should look at is, if I look at this exponential of iota HTMS R and then XA plus minus XB exponential of minus HTMS R, you should see what is coming here. It should be maybe with this or my plus or whatever it should be the case. And similarly, if you put PA plus minus PB, the same thing, what you will get is something like this, either this or this one. Okay. So, this is for you to figure out, I am not going to do that. You can figure out that this is the Hamiltonian, which will give rise to this kind of two mode squeezing. Okay. And yeah, so now what one can show is that if I appropriately choose, so for example, if I choose the 50-50 beam splitter, so like this, so the beam splitter corresponding to pi by 4, phi is equal to 0, epsilon is equal to 0, and then these two mode squeezing transformation, which I will call exponential of maybe I HTMS R, and then the UB dagger, Okay. This will be exponential of I H squeezing on R, this is single mode squeezing, tensor product exponential of minus I, or you can say I H squeezing with minus R, same thing. So, you see that after the action of these two beam splitter on two mode squeezing, it gives rise to these two single mode squeezing. So, therefore, once you can realize single mode squeezing, you can realize two mode squeezing and vice versa. Okay, so let me stop here.